Hey y'all, so I just wanted to quickly go over kinetics so that you guys had a better idea of the theory behind the experiment that we're going to be doing this week. Before you get into the lab, it'll make your post-lab questions and the experiment itself a whole lot easier if you have a better understanding of what's going on here. So the first thing to point out is that rates can be of either zero order, first order, or of a higher order. That would be second, third, fourth, and so on. With zero order meaning that rate is completely independent of the concentration of the reactants. First order being that rate and concentration of reactants are directly proportional. And second and higher order meaning that the small changes in concentration of your reactants have big impacts on the rate, whether that's of squared or cubed or so on. The second thing to point out is that there are two kinds of rate laws. There is the regular rate law that you think of, which is the differential rate law. That simply shows us the effect of concentration of reactant on how fast the reaction proceeds on average. So the overall rate of the reaction based on the concentration of reactants. And then we have what's called an integrated rate law, which shows us, given an initial concentration, how much reactant is left after a given amount of time. So the way to know which of these two types of rate laws to use is basically determined by our experimental setup. So if the concentration is easy to measure instantaneously, we can use integrated rate laws to determine the order of a reaction by comparing the concentration of a reaction over time versus the natural log of that concentration versus the reciprocal of that concentration. If it's not so easily measured instantaneously as the reaction proceeds, then we have to consider all of the reactants and compare them in varying concentrations in order to determine which ones affect the rate of the reaction more than the others. So in our experiment here, we're going to be working with integrated rate laws because our compound, crystal violet, is a pigment that is easily measured using a spectrophotometer. So our reaction overall is going to be using hydroxide and reacting it with crystal violet in order to make a complex. I'll just abbreviate that as CVOH here. The important thing to note is that crystal violet is purple, whereas OH and CVOH are clear. So as hydroxide reacts with crystal violet, there is going to be less and less pigment in your solution. So as y'all saw in the Beer's Law online lab, the amount of light that a colored compound in solution absorbs is directly proportional to its concentration in that solution. So in this lab, we aren't even going to worry about constructing a Beer's Law plot because we already know that there is a one-to-one correlation between those two values. So we can just substitute, instead of worrying about the concentration at a given time, we can just worry about the absorbance at a given time. Now, for y'all's lab, the way that we are going to determine the order of the reaction, whether it's 0, 1, or 2, is basically by constructing three graphs as our reaction proceeds. So the three graphs we're going to create are going to be using these three different types of integrated rate laws. So we're going to have the concentration of crystal violet as represented by absorbance versus time, the natural log of that concentration versus time, and then the inverse, or the reciprocal of that as we go through time. So what you're going to see is several data points as we go through time on each of these graphs. And using LabQuest, we're going to construct a line of best fit, just like we did last week. And what we're going to see here is that, of course, with the concentration and the natural log of the concentration, it's going to be going down because there's going to be less crystal violet as we go through time. And then, of course, with the inverse, it's going to be the opposite. It's going to be less inverse of the absorption, or more transmittance, going to less. So the way that we're going to determine which of these is the right one is taking advantage of the form of these integrated rate laws. If you haven't noticed, these take a very similar form to a general linear equation, y equals mx plus b, where b, our y-intercept, is simply what you started with. So that would be represented right here, and right here. Y is, at any given time, what the concentration is, x being that time at which we are measuring the concentration, and then m is going to be our slope of this line. As you can see, the slope is negative in the first two, in the zero order and first order, and positive in the second order, so they should be going down, down, and then up for the third one. And whichever of these lines best fits our data, that's going to determine the order of our reaction. The way that you visualize or quantify the closeness of the linear fit to your data is with a value called r. Now, r could be a negative or positive value, so we're going to square it so that it's always positive. And the closer that value is to 1, that is going to determine which of these plots is more accurate for the data that you've been recording. And so if say, our squared value for this first one is maybe something like 0.98, for this second one is maybe something like 0.96, and this third one is like 0.99, well, then it's more likely than not that we're dealing with a second order reaction, because that is the r squared value that is closest to 1, meaning that this line fits this data the best of all of them.